We have the third stage, which is the instruction decode stage, with the goal of converting x86 instructions into micro-ops. Here, the core decoder translates instructions into one or more micro-operations, and simple instructions map directly to a single micro-op, while complex instructions may become multiple micro-ops. Now, micro-ops are simplified, low-level instructions that the CPU can directly execute. Micro-operations break down complex x86 instructions into basic, predictable operations like load, store, and arithmetic operations. Since x86 instructions are complex and variable length, micro-op helps the CPU handle them more efficiently. Now, the core decoder is the component of the CPU responsible for analyzing the binary instruction stream and converting it into micro-operations. It identifies instruction patterns and applies any prefixes and uses built-in microcode routines when instructions are too complex for direct decoding. As I said, simple instructions map directly to a single micro-op, while complex instructions may become multiple micro-ops. Now, an example of a simple instruction is an instruction like add EAX1. So this would be a basic arithmetic operation requiring only one micro-op. Increment the value in EAX by 1. An example of a complex instruction might be rep move SB, which copies a block of memory byte by byte, requiring multiple micro-ops. One micro-op to fetch the next byte, another micro-op to move the byte to the destination, a third micro-op to decrement the counter and check for loop termination. Complex instructions like this rely on the microcode sequencer to generate the necessary series of micro-ops. So in stage 3 of instruction decoding, the decoder types might be the simple decoder handling one-to-one instruction to micro-op mapping, or the complex decoder breaks CISC instructions into multiple micro-ops, or the microcode sequencer handling rare or complex instructions using microcode ROM. Now remember, ROM is read-only memory, a non-volatile storage area containing predefined, unchangeable instructions the CPU can use to handle complex or uncommon instructions. Microcode ROM is used here because certain x86 instructions are too complex for standard decoding logic. So the CPU references these built-in microcode routines to generate the correct series of micro operations without needing to decode them from scratch each time. It's using microcode ROM because the x86 architecture supports a wide variety of instructions, including legacy operations from older CPU generations. And microcode ROM stores predefined micro-op sequences for these complex or infrequent instructions. This approach simplifies decoder design and improves performance by reusing microcode patterns instead of recomputing them on demand. So the performance impact here in the instruction decode stage, stage 3, is frequent use of complex instructions can strain the decode stage. And Intel's decoded stream buffer, DSB, caches micro-ops to avoid redecoding. Now the DSB, the decoded stream buffer, is a specialized micro-op cache in modern Intel CPUs. Its primary function is to store micro-ops that have already been decoded from x86 instructions. By retrieving micro-ops directly from the DSB, instead of decoding instructions again, the CPU saves time and resources, improving performance for frequently executed code. So you can think of it like instead of retranslating a complicated recipe every time you cook, you write it down once, that's a decoded micro-op, and refer back to it with the DSB whenever you need it. The DSB works by instruction decode stage decoding the x86 instructions into micro-ops. These micro-ops are stored in the decoded stream buffer if the instruction is part of a loop or frequently reused code, and the CPU retrieves the micro-ops directly from the DSB instead of rerunning the decode logic. It improves performance as decoding x86 instructions is resource intensive due to variable length instructions, complex instructions requiring multiple micro-ops, and prefix analyses and boundary detection overhead. By serving micro-ops directly from the DSB, the CPU reduces the workload on the decoders, minimizes stalls, and accelerates instruction throughput, particularly in tight loops. Now, the DSB improves performance but certain factors can cause performance impacts when it's used. There are DSB misses. That's if the CPU expects micro-ops in the DSB, but they're not there. It can cause a DSB miss. And then the CPU would have to fall back to regular decoding, introducing a stall. And you have DSB flushes, where microcode updates, context switches, or specific instructions might invalidate micro-op cache entries, requiring the decoder to restart the decoding process. And that instruction mix complexity, because the DSB is optimized for simple, repetitive instruction patterns like loops. Irregular instruction sequences, or complex CISC instructions, might bypass DSB caching, forcing full decode cycles. And there's branch mispredictions, where the DSB aligns micro-ops along predicted execution paths, but if the branch predictor fails, micro-ops become invalid and the CPU pipeline stalls. So as part of that stage 3 instruction decode stage, attackers can probe the decoder behavior to identify instruction boundaries or bypass security hooks. And instruction decoding anomalies can indicate malicious code injection. Attackers perform this bypass by analyzing CPU instruction patterns, cache behavior, and micro-op activity to infer how the decoder processes instructions. Using timing analysis tools, disassemblers, and side channel attacks, attackers can map instruction boundaries and identify security hooks placed by antivirus engines or intrusion detection systems, IDS. This information can help craft obfuscated payloads, evade detection, or manipulate CPU behavior by exploits like speculative execution attacks. Probing decoder behavior involves observing how the CPU's instruction decoding process reacts to different instruction patterns. The goal is to identify instruction boundaries, to obfuscate malicious code, to bypass security hooks like inline hooks from EDRs and antivirus software, and detect micro-op behavior anomalies to leverage microarchitectural attacks. They use techniques like cache timing analyses, micro-op cache probing, DSB exploitation, where the micro-op cache stores decoded instructions to improve performance. Attackers probe those micro-op cache hits and misses to identify instruction patterns and distinguish between simple and complex instructions, allowing malware to adapt its code structure to avoid detection. And they use prefix manipulation, like we've talked about, and hook discovery via decoder behavior analyses. So endpoint detection and response systems and antivirus systems often inject hooks into critical functions like NT open process. Attackers probe decoder behavior by executing instructions near known hook locations and observing decoding anomalies. If the decoder stalls or cache patterns change, it's a sign of inline hooks or patching. Rootkits like Turla and Fin6 malware have been observed probing syscall interfaces for security hooks to dynamically disable or bypass them. Once attackers understand how the decoder processes instructions, they can craft those obfuscated payloads, bypass the hooks, and develop side-channel attacks. They do need skills like low-level assembly knowledge, x86 instruction structure, prefix usage, and decoding logic. Microarchitecture understanding like familiarity with micro-op caches, branch predictions, and instruction pipelines, and side-channel analysis proficiency, applying statistical methods to interpret cache timing variations. These are skills these hackers need. And tool proficiency with tools like the same ones security experts need. They could be Perf, Intel, PCM, Ghidra, and x64 DBG for a few examples. And just to clarify, a security hook is a mechanism used by security software like the EDRs and antivirus to manage, intercept, or modify function calls within application or the operating system. These hooks are strategically placed in key system functions to detect malicious activity like unauthorized process injection, to log system events like file access and network connections, and hopefully prevent execution of known malware patterns. When a legitimate program calls a system function like NT open process, the hooked version of the function intercepts the call and redirects execution to a security monitoring code. If the activity is safe, the hook will pass the control back to the original function. If it's malicious, the hook blocks the operation, logs it, or alerts security personnel. Inline hooks, function hooks, they're the most common. They inject code directly into the beginning of a function, redirect execution to security routines, and are often used by EDRs to monitor monitor API calls like ntCreateFile or virtualalloc_x. Import address table IAT hooks are common in malware and EDRs. They modify function pointers in a program's import address table, redirecting calls to security monitoring code. So createfile A originally points to kernel 32 DLL. Createfile A, the hook modifies the pointer to point to EDR monitoring code, for example. Then you have the syscall table hooks, which is kernel level monitoring, modifying the OS's syscall table to intercept low-level system calls. It's used by advanced EDRs to monitor processes, threads, and memory operations. OS operating systems, syscall table. Attackers can bypass security hooks with instruction boundary probing, hook removal and overwriting, and direct syscall invocation. I mentioned virtualalloc_x. That's a Windows API function used to allocate memory in a target's process's virtual address space. It's part of the Windows Memory Management API, and it's defined in that kernel 32 DLL library. Unlike virtualalloc, which allocates memory in the calling process, virtualalloc_x allows one process to allocate memory in another process, provided it has the necessary permissions. It works by a process obtains a handle to the target process via open process function. It calls the virtualalloc_x function to allocate memory in that target process's virtual address space, and this allocated memory can then be read, written, or executed depending on the protection flag set. It has both legitimate uses like remote debugging tools, inter-process communication between trusted processes, and game mods inject data into game process to alter behavior, and then malicious uses like malware leveraging to inject code into legitimate processes, code injection techniques like DLL injection, process hollowing, and reflective code injection. In that case, that's loading malicious code directly into memory without touching the disk, which we call fileless malware. The IAT, import address table, that's a data structure used by Windows executable PE files to resolve and manage function calls from external libraries, DLLs. When a program uses external functions like write file from kernel 32 DLL, it doesn't embed the code directly. Instead, it references the function via the IAT, import address table, which dynamically resolves the function's memory address at load time or runtime. Windows applications frequently use shared libraries, DLLs, to avoid code duplication and reduce application side. DLL stands for Dynamic Link Libraries. They provide common functionality like file operations, networking, and cryptography, and the IAT ensures the application can locate these external functions at runtime regardless of their exact memory addresses. So the IAT is like a dynamic phone book. The functions are the contacts and the table entries are the phone numbers. When the program needs a function, it checks the IAT for the correct memory address. However, because the IAT determines which code runs for imported functions, it's commonly targeted by malware to do things like redirect function calls. Malware modifies IAT entries to point to malicious code, injecting malicious payloads. Malware can inject code into a process and alter IAT entries to execute malicious functions, like a DLL injection technique often targets the IAT. And for bypassing security hooks, because security tools hook critical APIs via IAT modifications, and malware can remove or bypass these hooks to avoid detection. Security professionals detect IAT tampering with integrity checks, tools like GMER, GMER, or volatility to compare runtime IAT entries against their expected values, using sysmon event IDs like 10 and 13 for sysmon monitoring, and behavior-based detection, monitoring for unusual function call patterns like high-frequency calls to virtualalloc_x or write process memory.